Okay, so in our last lecture, we were kind of looking at the time-dependent perturbation theory. We are looking at the scattering problem from a time-dependent perspective. If you remember, we defined this interaction picture where the operators evolved under non-interacting Hamiltonian, whereas the states evolve under the under the potential only. And in this interaction picture, we had seen that the time evolution operator, let's say that if you know your state at the time t0, your state at the time t can be written in terms of this initial state in the interaction picture by the action of this time evolution operator, where we had also derived that ut t0 is actually equal to something that we define the time-ordered exponential of minus I dt prime vt prime. This is the potential in the interaction picture. So it is evolving in time, starting from t0 up to t. So this was our evolution. And we then looked at trying to calculate various corrections to our wave function. Well, there was one thing we had observed when we looked at the let's say initial final state scattering amplitude. We have an initial state. We let the system evolve, and we looked at the probability that it will be in a given state at a later time. We had seen that this amplitude is actually given by some 2 pi times the Dirac delta for energy conservation times some matrix element. Let's just call it T. And this T basically, if you remember what we had done over here was when we calculate, in fact, when we looked at the product of this probability and looked at the rate of change, the transition rate for this probability, this turned out to be proportional to some energy conserving Dirac delta times some matrix element squared. And if you remember what we obtained was that probability was given as the sine squared delta E times T divided by delta E. And then we said that in the limit of very large T, that sine squared becomes a this Dirac delta function. And then Dirac delta function times T, so the rate was constant. The total transition probability was proportional to time. The rate of transition was just a constant independent of time. So this was what we had obtained. And this T, again, we had obtained it. Well, this T over here was nothing but the T that we had also in the time-independent perturbation theory. So in particular, it satisfied this equation T for a given energy. This operator is V plus V times 1 over E minus H0 T. This was our equation. Then, of course, we basically recovered our time-independent perturbation theory result, etc. So any questions up to here? Now, when we actually calculated this T for the time-independent case, remember we started drawing these diagrams describing what is going on. There we also saw that we have an additional momentum conservation. So we can actually write this, let's say this is my initial state, I let it evolve, this is my final state. This is the so-called S matrix. This is equal to 1 plus I. I will get eventually some energy and momentum conservation, so I make it explicit. This delta P is sum of the form momentum of the final state minus sum of the form momentum of the initial state, whichever particles you have. Now we were interested in the scattering cross-section. Well, the scattering cross-section is essentially proportional to this rate. Now, in this case, we have also the momentum conservation. So the scattering rate will be energy momentum conservation for all our processes. Remember, the scattering rate was basically defined as the ratio of fluxes, flux going to my detector divided by the incident flux. And we have the overall energy momentum conservation. We have this matrix element square. Well, let me write this matrix element. Let me use a different symbol. We have m squared. That is basically the probability of a transition. When you factor out the energy momentum conservation, well, the states that we have are usually not normalized to 1. Remember, we are normalize it to twice the energy. So we have to fix that normalization if we would like to have the momentum, a probability interpretation. So we have to divide by, let's say, the product of twice omega E over the initial particles, or the energy of the initial particles twice the energy of the final particles. And then, okay, our detector doesn't measure a single momentum. It will have a finite area, so any particle scattered within that area will be measured by my detector. So when I'm measuring the cross-section, I will not be measuring a single final momentum of the single state, but I need to sum over all the final states that I'm actually measuring. So I have to sum over all the final particle momentum, and then divide by the flux, incident flux. Let me just write it phi. Well, this is the general expression for our cross-section, actually. Now we can have, for example, two particles scattering into two particles, as a concrete example. In this case, the scattering cross-section will be 2 pi to the 4, the energy momentum conserving Dirac delta, m squared divided by, let's assume that I'm looking at this scattering cross-section in the rest frame of one of the particles. So that will be, then I need to divide by twice energy of the first particle, the energy of the second particle, which is at rest. The flux will be just the speed of the particles, v. And in the final state, I have two particles. Now I also need to divide by the normalization of the final particles. Let me write twice omega p1, twice omega p2 over here. I use E and M for the energy of the initial particles and omega for the energy of the final state particles. Now, if you look at one of these, well, this is basically called the Lorentz invariant phase space. My detector will not measure just a single point in the phase space, but it will measure a region in the phase space. And that is the phase space factor that my detector will measure. Now, how do we know that it is Lorentz invariant? Well, let's look at this one. D4P Dirac delta m squared minus p squared divided by 2 pi to the 4 times 2 pi over there. Let's look at this integral. Well, I have 4 integrals over there. This is definitely Lorentz invariant. The argument of the Dirac delta is Lorentz invariant. D4P is the Lorentz invariant for volume in the Minkowski space. Or if you can also imagine it as if you take a boost. If one component is compressed by gamma, the other one will be extended by gamma. So this will be invariant. So just like if this was in coordinate space, length contraction and time dilation factors will just cancel if you just boost it, these dp's, dx's in that case. So that's also another way to see that d4p is actually invariant. But I repeat, this is in flat space. The metric has a determinant of 1. If it was not flat space, I need to also add that one, the metric. So this is Lorentz invariant. Let me add also theta p0. Well, this just tells me that only consider the space with positive 0 component. Now that factor, although p0 is not Lorentz invariant, that factor is Lorentz invariant. If the 0 component of a 4 vector is positive, then it is positive for every observer. Its value might differ, but it will always be positive. So that theta p0 is Lorentz invariant. So everything appearing here is Lorentz invariant. Now, let me separate the 0 component integration and the other integrals. dp0. I have Dirac delta omega p squared minus p0 squared. p0 goes from 0 to infinity. Now there's just one point in that p0 integral that will contribute to my integral, which makes the argument of the Dirac delta 0, and that result will be d cubed p divided by 2 pi cubed times that integral will just give me 1 over 2 omega p. So this is Lorentz invariant. So we started with a Lorentz invariant expression, and hence this answer has to be Lorentz invariant. That is why we have this is a phase space integration, and it's a Lorentz invariant phase space integration. And remember, d cubed p1 and d cubed p2 were basically looking at what my detector is actually measuring when it is measuring the cross section, and that 2 omegas actually came from the normalizations that we use. That was in fact one of the reasons why we didn't normalize it to 1, the states, but twice the energy. Well, here almost everything is Lorentz invariant. You see 4 vectors are equal to each other for one observer. They will be equal for every observer. So this Dirac delta to the 4 is Lorentz invariant. Cross section, remember it's an area. Area is not a Lorentz invariant quantity. But keep in mind that what we are looking at, let's say that we are looking at a head-on collision, or in this particular case, the way I wrote it, I'm looking at one particle is at rest, the other one particle is colliding with it. And this area is an area perpendicular to this line. So this cross-sectional area will be invariant for boosts along this line. So that will be invariant for boosts along this line. So whether I do head-on collisions or fixed target collisions, this cross-section will be the same. Should be the same. And well, this flux factor I wrote was for the specific reference frame in which one of the particles is at rest. So I would rather write that also as an expression that is valid for in any reference frame. So let's try to do that. So this is E1 is the energy in the fixed target in the lab frame, let's say. 2m2 is the mass. Times this is the speed of the first particle in the lab frame. The other particle is at rest. Well, I can write this as twice p1 times twice m2, because the momentum of a particle is just its velocity times energy, or velocity is linear momentum divided by the energy. In this particular reference frame, the form momentum of my first particle is E1, P1. My other particle is M2, 0. This is what I have in the reference frame, in the lab frame. Well, let's see. If I look at, let's say, P1, P2, that for product is E1 times M2 or E1 will be equal to P1, P2 divided by M2. You see, in this expression, this is the right-hand side is a Lorentz invariant. It's the scalar product of two vectors. So just go to whatever reference frame you would like to, you are doing your experiment. Measure the four vectors P1 and P2. Multiply, consider their scalar product and divide by the mass of the second particle. What you will obtain will be the energy of the particle in the reference frame in which P2 is at rest. No, the energy of the first particle in which, yeah. Okay. So the right-hand side, just calculate it in whichever reference frame you want. That will be the energy of the particle in the reference frame in which the second particle will be at rest. Well, let's look at P1. E1 squared minus P1 squared is M1 squared, or P1 is actually E1 squared minus M1 squared square root. Well, I know P1. This is P1, P2 squared divided by M2 squared minus M1 squared. Which will be square root of P1, P2 squared minus M1 squared, M2 squared. This is my P1. Well, what is my flux factor? Remember, this is my flux factor. Divided by M2. The flux factor is which is nothing but 4 P1, P2 squared. Well, if you like, you can also write P1 squared, P2 squared. This is the incident flux when I'm colliding two particles. Note that this is Lorentz invariant. So now I can write the scattering cross-section as 2 pi to the 4 Dirac delta delta P. This is the energy momentum conservation. The matrix element squared divided by 4 times this square root times Lorentz invariant phase space factor. So any questions here? You see, what we had done is I just identified the transition matrix element, separating out the energy momentum conservation. It will be always there. And then the scattering cross-section will be the transition matrix element without the energy momentum conservation squared. I have the energy momentum conservation. You see, that's not something I put by hand. That comes from the derivation, just like we did the explicit energy conservation. But momentum conservation, Dirac delta, also comes from the derivation itself. That's not something I put by hand. Then I have to correct for the normalizations. I have to sum over all the final states that my detector is measuring. And then I have to divide by the incident flux. And that incident flux is just, if you are sending just one particle on one particle, that is V. Just the velocity of your system. And then you can also write the flux V in a Lorentz invariant form. You see, this expression, everything appearing in that expression is Lorentz invariant. So you can just go ahead and calculate in whatever reference frame you want. In the lab frame, in the center of mass frame, you will always get the same answer. Well, let's see, how do we integrate over this Lorentz invariant phase space factor? Well, let's try to do that. D cube P1 divided by 2 pi cubed twice omega P1. D cube P2 divided by 2 pi cubed twice omega P2. 2 pi to the 4, Dirac delta to the 4, P1 plus P2 minus, let me just call it the total P. This is my energy momentum conservation. This is the Lorentz invariant phase space factor for a final state containing two particles. Well, I can just choose any reference frame I like to evaluate this integral. Let's just choose the center of mass frame. Well, in the center of mass frame, that Dirac delta will be equal to, the zero components will give me omega P1 plus omega P2 minus energy in the center of mass frame times the three-dimensional Dirac delta of P1 plus P2. So now I can evaluate the three of those momentum integrals, which will give me 1 over two pi squared. I just simplified all the 2 pi factors. Let me evaluate the P1 integral, and let me then for P2 I will have omega P2 divided by d cube P2 omega 1 P2 omega 2 P2. Now, they can be different particles. Their masses might be different. So even though their momentum are the same, just pointing in opposite directions, their mass can be different. So the omega 1 P2 and omega 2 P2 will be different. Let me just write omega 1 and omega 2. Where omega 1 is square root of P2 squared plus M1 squared, omega 2 is P2 squared plus M2 squared. They both have the same free momentum. They correspond to both particles have the same free momentum because I'm in the center of mass frame. And I have this, and then I also have Dirac delta omega 1 plus omega 2 minus E center of mass. I can go to use spherical coordinates. So this I, remember this I will also obtain m squared, etc. This will be 1 over 2 pi squared P2 squared dP2 d omega 2. Let me write di d omega 2 divided by omega 1 omega 2 Dirac delta omega 1 plus omega 2 minus E center of mass. So the I by the omega 2. This is the direction of the second particle, the scattering cross-section for the second particle to scatter in this direction, omega 2. I don't care about the energy. Let's say I'm just looking at the direction. That means I need to integrate over all momenta. So it will just give me 1 over 2 pi squared dP2 P2 squared divided by omega 1. Remember, these all depend on P2. The Dirac delta also depends on P2. Now I have one integral, one Dirac delta. Well, I can evaluate this integral using that Dirac delta. The result will be 1 over 2 pi squared P2 squared divided by omega 1 P2 omega 2 P2 1 over omega 1 prime with respect to P2 plus omega 2 prime with respect to P2 evaluated at the value of P2, which will make omega 1 P2 plus omega 2 P2 is equal to the center of mass energy. I can do a bit more. You see, omega is square root of P squared plus M squared. So omega prime will be P over omega. I can take those derivatives. This is so-called the differential cross-section is equal to 1 over 4 pi squared P2 squared divided by omega 1 P2 omega 2 P2 1 over P2 over omega 1 plus P2 over omega 2. Well, one of these P2s cancelled with P2 squareds, and then I have 1 over 4 pi squared P2 over omega 1 plus omega 2, which is 1 over 4 pi squared P2 over E center of mass. So if I would like to obtain the differential cross-section for two particles scattering, d sigma over d omega, let me put the 2. This will be m squared over 16 pi squared, that's square root, times P2 over the energy of the center of mass. Now, we said that let's evaluate this in the center of mass frame. In the center of mass frame, P1 is equal to E1P, P2 is equal to E2P, E2 minus P, because I'm in the center of mass frame, P1, P2, E1, E2 plus P squared, and E center of mass is equal to E1 plus E2. Well, you can just go ahead and simplify as much as you want. But this is just our cross-section for differential cross-section for two particle scattering. And why do we do the scattering amplitudes? Well, we would like to learn something about the dynamics. And what this tells me is that just by looking at the angular distribution of these scattered particles, I can calculate this matrix element squared. Because all the other factors are just kinematical factors. E center of mass is the energy I send my particles to collide with. P2 is the momentum of one of the particles, which I can measure in my detector also. And well, everything else except an m squared is just fixed by the kinematics. I can measure the cross-section, I can measure the kinematics of the scattering process, which gives me m squared. And remember what m is. In first order, in the Born approximation, this is just the matrix element of the potential. But this matrix element is nothing but, if I use plane waves, that is just the Fourier transform of my potential. So if I can determine this m squared as a function of q, well, I'm actually measuring the potential that these two particles are interacting with. Of course, higher orders will give higher order terms. Those will basically modify the interaction potential between these two particles. By the way, although I calculated this integral, you see, this is an integral I calculated in the center of mass frame. And I already know that at least the integral I is Lorentz invariant. I can also express it in different ways so that it does also look Lorentz invariant. You see, I have particles coming in, let's say with momentum k1 and k2. Something happens, particles coming out with momentum p1 and p2. P1 will be the 4 vector, will be E1, omega 1 times P2 minus P2, and P2 is omega 2 P2. I'm in the center of mass frame, the total linear momentum should be 0. E center of mass will be omega 1 plus omega 2, which is the square root of P1 plus P2 squared, the total momentum. P2, the magnitude of P2, I can say that this is equal to omega 2 squared minus m2 squared, because omega is mass squared plus the momentum squared. Omega 2, I can write it as P capital P times P2. Capital P is P1 plus P2 or K1 plus K2. In the center of mass frame, capital P is just E center of mass and 0. So E center of mass squared is P squared, that is what I used over here. And omega 2, this one only, will be P2 times capital P divided by E center of mass. So P2 will be divided by square root of P squared, this is omega 2, this whole thing squared minus m2 squared. Now this is now everything is Lorentz invariant. Well, I might be more tempted to describe this process. Let's say I have collisions coming in. These are the particles colliding, then they will scatter in some other direction. Let's say this is the scattering angle. I might want to express everything in terms of this. Well, in fact, I already have everything expressed in terms of this scattering angle. Remember, this is what I calculated in the center of mass frame. So I can choose this as my z-axis. So the omega will be actually d phi sine theta d theta. If nothing depends on phi, I can integrate over this, so the omega will be 2 pi sine theta d theta. Usually everything is expressed in terms of q squared. Remember, even my matrix element is actually a function of Q only. So if V of R is spherically symmetric, this integral will depend only on Q squared. Everything depends only on Q squared. So I should be better express everything in terms of that Q squared. Well, let's see, what is Q squared? This is, let's see, this is K1, this is K2, this is P2, this is P1. P2 minus K2 squared, this is the change in the momentum of our particles. Whichever one you prefer, this is the momentum, momentum transfer to any one of them. And, well, if you like, you can let's say in this reference frame, now K1 is E1 K, K2 is E2 minus K, P1 is omega 1 minus P, and P2 is omega 2 P. Now what is Q squared? Well, that will be P2 minus K2 is omega 2 minus E2, and P plus K squared, which is omega 2 minus E2 squared minus P plus K squared, which is omega 2 squared minus P squared plus E2 squared minus K squared. And then I have minus 2 omega 2 E2 minus 2 P K times cosine theta. Now, this is Lorentz invariant. Now what I'm trying to achieve is to show, at least I will not do all the derivation, but to show that I can write everything in terms of Q squared. You see here, this is, the first one is omega 2 squared minus P squared is just M2 squared plus M1 squared minus 2 omega 2 E2 minus 2 P dot PK cosine theta. P is fixed. This is E center of mass 0. Well, I already know what omega 2 is. This is P, capital P, times P2 divided by E center of mass. Capital P is also P1 plus P2. Which will be, no vector over here. This will be P1, P2 plus P2 squared divided by E center of mass, which will be 1 over 2 P1 plus P2 squared minus P1 squared minus P2 squared plus P2 squared divided by E center of mass. So omega 2 now is a function of E center of mass Now, omega 1 is a function of E center of mass only, which I can also write as square root of P squared. center of mass is something that I chose when I was making these collisions. So this is for omega 2. Now if I go back over here, okay, this is already Lorentz invariant, this is Lorentz invariant. Omega 2 now expressed in terms of a Lorentz invariant quantity that depends only on the center of mass energy. I can do basically the same thing for E2. But if I know omega 2, remember P will be omega 2 squared minus M2 squared. I have omega 2 in terms of the center of mass energy. This is Lorentz invariant, which tells me that P is now expressed in terms of the center of mass energy. So let's go back. This is now Lorentz expressed in a Lorentz invariant way in terms of the center of mass energy. I can do the same thing for K. Well, Q squared is cosine theta. So that will allow me to express cosine theta in terms of Q squared. In particular, dQ squared will be 2pk d cosine theta. And remember, d omega is 2 pi d cosine theta. So which tells me that d omega is actually dq squared times pi over pk. Okay, again, I will not do the derivation, but basically I wanted to show that you can express everything in terms of Lorentz invariant quantities. The typical Lorentz invariant quantity that we use is the momentum transfer squared. Already we had evaluated the integral. Yeah. Okay. This is in a specific reference frame, the center of mass frame. I can convert everything into, including omega 2, to a Lorentz invariant quantities. And once I do that, well, I can just calculate the cross section in whichever reference frame I like. In fixed target experiments, in symmetric experiments, there are also asymmetric collisions in which the momentum are not the same. One beam has a slower momentum, the other beam has a larger momentum. Well, the advantage is kind of the created particles will have a momentum, so if they are short-lived, thanks to time dilation, they will be moving, they can move a significant amount of distance, and hence it will make it easier to measure them. Now, before we go for a break, let me also discuss the lifetime, the differential decay width. So, okay, here before in cross-section we were looking at colliding two particles, and then at the end we have two or more particles. That's what we call the scattering cross-section. But we might be also interested in, for example, what happens when you have an unstable particle. So you want to study how fast it will decay. Now, it's again a transition, just like the scattering process. It's a transition process, and you want to know how fast it happens. Well, there will be a probability. Well, this is the probability of the decay. Energy momentum will still be conserved. But this time in the initial state, there's a single particle. Well, the decay rate is usually defined in the rest frame of the particle. So I now need to correct for the normalizations. Well, there's a 1 over 2m. This is the mass of the decaying particle. And then the final products, well, they can move in various directions. We can just dqpf over 2 pi cubed 2 omega f. This is our Lorentz invariant phase space factor. Again, that 2 omega f comes from our normalizations. Integral over the final state momentum. Well, my detectors looking at the decay of this particle will not measure a single well-defined momentum. They will measure some spread in momentum. So since decay rate is defined as the number of decays, so I'm just trying to count all the decays, I need to consider the fact that my particle can decay into different particles with different momentum. So I need to integrate over all possible final momentum of my particles. So this kind of concludes, in the last few weeks, we were mainly discussing what are we trying to calculate using field theory. Okay, we will study field theory, but what will be our purpose? So that kind of concludes our purpose. We will be eventually interested in calculating this thing. How can we calculate that? And remember, that will be related to these matrix elements. I assume that my particle is in a given plane wave state. In the final state, it will be also some other plane wave. I will be calculating these transition amplitudes. We had already done one example in the time-independent perturbation theory case. Now we will try to generalize it to arbitrary processes, which might involve arbitrary number of particles in the initial state, arbitrary number of particles in the final state. So any questions before you go for a break? Okay, so let's give a 10-minute break and we will continue with more computations.